Hi, good morning, everybody. Welcome to Thursday morning's plenary session. Today I have a couple of pre-plenary announcements, and then we will go ahead with our science keynote speakers. So as always, and as you know by now, we have a code of conduct for this meeting. If you experience or witness anything that feels like a violation of the code of conduct, please go to the Project and Community Workshop website. Click on the code of conduct. You can review it there. And also you'll find contact information for our workplace culture advocates, and they're the ones to whom you report the violation of the code of conduct, and they will help you with that and advise you on what you might be able to do next. Other friendly reminders are that all talks at this workshop are recorded unless otherwise requested. If you don't want to be recorded, you can keep your camera off. Videos are posted the next working day. It does take some time to prepare those videos. As we do questions from the Slack channel, please do give a thumbs up or some kind of other emoji to the questions if you have the same question or you particularly like that question. And that kind of ranking helps us prioritize questions when we ask them to our speakers. And also, of course, in the Zoom as well, remember that you have reactions and you can provide applause that way. So a couple of announcements to start. First, all session chairs, please remember to fill in your summary slide for the Friday breakout summaries session. You'll have a link. Rand Paul will contact you with a link for that slide deck. Second announcement is that a new session was added today at 12 p.m. It's called Engaging with Ruben Observatory, and in that session, the Rubin community engagement team will cover resources for learning more about Rubin and the future data products, and where and how to ask questions and how to interact with the Rubin community. We'll also be giving a tour of the community.lsst.org community forum. Everyone's welcome to join this session today, and there'll be plenty of time for Q&A. Third announcement is that the anti-racism workshop it starts today and it goes today and tomorrow. It's limited in number, and participants, you should have all received the Zoom link by email already. There are 4 sessions if you are a participant, 2 one-hour sessions today, 2 one-hour sessions tomorrow. And it's not open. They're not accepting any more new participants in that workshop. So let's get started with today's plenary, the science keynote. So this year, the Science Organizing Committee has invited Dr. Chihway Chang and Dr. Elisabeth Krause to speak about the Dark Energy Survey, or DES. This is timely because earlier in 2021, the DES released their Year 3 cosmological analysis, and the DES continues to have science impacts well beyond cosmology. Dr. Chihway Chang is an assistant professor at the University of Chicago who received her PhD in 2013 from Stanford. She's an observational cosmologist and survey scientist working primarily on cosmology with weak lensing in large galaxy surveys. Dr. Elisabeth Krause is an assistant professor in astronomy and physics at the University of Arizona. She received her PhD in 2012 from Caltech. Her research of combining different cosmology observations is at the intersection of observation and theoretical cosmology. Both of today's speakers are or have recently been DES Science Committee chairs. So from there, I'll invite, I think Chihway is speaking first. Go ahead. I'm going to stop sharing so that you can take over.
All right, you see my cursor?
Yes, yeah, I do.
Great, so thanks Melissa for the introduction and the invitation, and thanks everybody for tuning in. Good morning, good afternoon, good evening, depending on where you are. Today, as Melissa said, Elisabeth and I will tag team to tell you about a very wide range of sciences that you can do with the survey. We're talking about the Dark Energy Survey, but obviously LSST will do the same and better. As Melissa said, my name is Chihway Chang. I'm assistant professor at University of Chicago. I'm one of the 2 science committee co-chairs together with Michael Troxel at Duke. And we recently took over from Elisabeth and Scott Dawson at CMU as the previous science committee co-chair. But everything we talk about today comes from a much larger group of people, especially early career scientists that we can't enumerate here. but many of them are in the audience and you're welcome to reach out to them about their science. Okay, so we're going to start with a brief intro to bring everybody on the same page, and then I'll cover kind of a very broad range of kind of non-cosmology science, going from solar system all the way to cosmology. And then Elisabeth will go in deeper to this year 3 cosmology results from large-scale structure that Melissa mentioned that we recently released. And then we have a little bit at the end to give our kind of take of lessons learned from the DES experience and how that might help thinking about LSST science. And we'll have some Q&A at the end. Okay, so DES is a photometric galaxy survey. It is conducted using the Blanco-Fourmier telescope at Cerro Tololo. You can see a map over here. It's outside La Serena, across the street from Cerro Patron, which is where Rubin and Gemini South are. It uses the dark energy camera, DE-CAM, which you can see over here as the focal plane. It spans 3 square degrees field of view with 70 4K by 2K CCD chips, which adds up to 570 megapixels, and we survey in 5 bands, GRI, ZY. I listed the Rubin LSST camera's numbers down here so you can compare. Basically, LSST is a bigger, better version of DES. Here's showing that the dome, the Blanco dome, and inside the dome, the telescope. The survey itself is 5,000 square degrees in terms of footprint in the south. It observed 2013 through 19, so it's finished. It contains the same as DES Y field and supernova fields, and it overlaps with many external data, including South Pole Telescope, Atacama Cosmology Telescope, Stripe 82 from SDSS, and so on. The recent data release, DR2, which contains all 6 years of data, contains 550 mega galaxies, 145 mega stars, and down to a limiting magnitude of R of 23.5. All this data is public. You can reach it at this NCSA slide over here. And again, I listed the LSST numbers for your comparison. Here's showing a image of the footprint. Sorry, let me move the zoom window. You can see that our footprint is south of the galactic plane. It's at reasonably high galactic latitude. It overlaps with SPT's footprint on the south and Stripe 82 on the north. It has this funny looking tank shape. Whenever you hear people refer to DES year 1, it's the first year data that comes mainly from the south in this yellow patch, whereas year 3 covers the entire footprint, and year 6, which is the final kind of DES data, will be the same footprint but deeper. Okay. Right, so DES obviously is made up a lot of people. We have 400 scientists from 25 institutions in 7 countries, and this number is constantly growing. Something we're really proud of, which Elisabeth will mention again later as well, is that we have a lot of early career scientists leadership in the collaboration that really took on the role of leading all the science. And if you kind of want a sample of some of the fun facts or some of the people in DES, we have a reasonably active outreach program that you can kind of click on these links. We'll share the slides later, where there are programs that look into different scientists, different published papers and public writing, and then some social media venues. And of course, we're now all super used to Zoom meetings. This is the last collaboration meeting in May. You can see everybody is reasonably happy. Okay, so as I said, DES science spans a very wide range. Here on the left, you can see kind of the type of objects we look at. And it ranges from solar system objects, Milky Way, galaxies, supernova, weak lensing, strong lensing, all the way to like distant quasars. So really we're spanning a huge redshift range from redshift 0 to like distant quasars, redshift about 5, 6, 7, from very small objects in the solar system to galaxy clusters of 10 to the 15. So it's a wide range of things we just get in our data because it's a survey telescope. And with that data, DES kind of is founded or driven by cosmology, but you can also do many different things like particle physics or astrophysics related to different systems. So really, my whole point here is that I want to make the point that surveys are great, and really the kind of science is probably more than what you can predict right now. So many things I'm going to talk about later was not by design, but they came out of the data, and we're reasonably confident that LSST will do the same and more. Okay, so following, I'll spend the next like 15 minutes highlighting some recent DES science results. It's very incomplete, so I apologize if your favorite science was not listed. And if you're really interested, there's of order 360 papers that you can read about all the science. You can click on this link. I think it's still not exactly complete, but it has most of the papers. And one thing I do want to highlight is I'm going to talk mostly about science, but really behind the science, there's a vast kind of pool of tools and techniques and methodologies that was developed through doing these science. And that really is one of the main kind of legacies of DES. Okay, so I'm going to step through starting from stuff really close by to stuff really far away. So we're starting from the solar system. So who would have thought DES is actually a really powerful tool to do transient science? And this is beyond the supernova fields that was designed to find supernova. This is basically the whole big wide field area. The reason being, of course, at any given part of the sky, there's multiple exposures. And if you detect an object in one exposure and not the other, you basically have some clues to find transients. So the kind of case I'm highlighting here is work done by a Penn grad student, Pedro Bernardinelli, and Gary Bernstein, professor at Penn, who basically conducted this wide field search to look for moving objects. And they basically found the candidates and then tried to link the objects through orbits and then make some reasonable signal noise cut on the orbits to then define this catalog of 815 transit-Neptunian objects. This catalog is only 3 objects less than the biggest TNO catalog ever exist. And basically DES added 20% more TNOs to human knowledge. So that's pretty impressive. On the right, you're seeing basically distance and magnitude, and each of these points is a TNO. So from year 4 to year 6, we got deeper. That just shows on this. Okay, I want to show this movie because it's really cool. It's basically the same analysis I talked there. It's a movie made by Penn student Sarah, which you can see here that there's this object over here. That is the moving object. It got detected. And then you can predict where this object might be going, and then find the orbit linking the different detections. So each of the flash is a detection. Okay, zooming out, we can look at multiple objects. So there are these 5 TNOs. Again, each flash is a detection, and you can see they're clustered based on when DES is looking at that region. This early pattern comes from the Earth rotating. You can see this zooming out again. You can see the DES footprint and all the 700-800 TNOs rotating together. You can see the flash. The colors is the distance from us. Okay, further zooming out, you can see the relation with the solar system. And then these things are just basically going out their merry way of rotating. Okay, this movie is super mesmerizing. I'll stop it here. Feel free to go back and look at it. It's super cool. And again, something that we didn't think we would be looking at. All right, out of the search, another surprise was that these folks actually found a comet. So this was the big press release you probably have seen maybe a month ago. This comet is now named after Pedro and Gary, and it is the largest well-studied comet to date. It's the most distant comet to be discovered on the incoming path, and it will make its closest approach in 2030. And in general, these objects, both comets and TNOs, help us understand the formation of the solar system and how it connects with the Oort cloud. Okay, so stepping out a little, now let's look at the Milky Way. Similarly to kind of the TNO science, Milky Way is a big discovery space using DES data. So here's just kind of an example of objects that we look for in the Milky Way, so in the DES data sets in the Milky Way. Just to make the point that this is a massive discovery space, I put here two plots from Alex Wagner and Ting Li, showing basically the history of discovery of Milky Way satellites and stellar streams as a function of time. And you can see each of these jumps associates usually with a big data set. And DES essentially doubles the number of Milky Way satellites and adds a significant fraction of stellar streams as well. These are two kind of spin-off surveys I'm pointing out here. One is to spectroscopically follow up streams, and one is to look at just the whole Southern Hemisphere local volume objects through the STEL survey that you can click on it later. Okay, so after you have all these objects, what do you do with it? Here's an example. This is work done by Ethan Nowther, a previous PhD student at Stanford. So he took all these Milky Way satellites and took the position-dependent Milky Way satellite luminosity function to constrain different dark matter scenarios. So here is showing three classes of dark matter candidates: stellar neutrino, warm dark matter proton, scattering, interacting dark matter, and then ultralight axion fuzzy dark matter. The constraints from DES plus pan-stars is these red curves. And then there's other constraints from other probes kind of on the plots in different directions. So the main message is just that DES is providing very comparable and better constraints on dark matter models, which is like fundamental physics, by looking at these Milky Way satellites. And compared to other methods, we can now combine them together and provide very good constraints. Another thing we like to look at in the Milky Way are these stellar streams, which I mentioned earlier. This is an animate showing what they actually are. So they're basically these star clusters that get torn apart and stretched out on the sky as streams. And as such, they're really good probes of the gravitational potential of the Milky Way, as well as dark matter substructure. So this is work I'm highlighting from a student, Nora Ship, who basically conducted such a stream search using kind of star distribution on the sky convolved with the isochrone at different distances. So if you look at the right-hand side, this is stepping through different distances. And you can see different streams kind of light up as you step through different distances. Because these streams come from these star clusters, they have the same isochrone, so they pop up together at a given distance. So through this search, Nora found several new streams in the Southern Hemisphere, and she's now leading kind of the follow-up of these work. Okay, stepping further out, now let's look at galaxies. I'm a cosmologist by training. So I usually think about galaxies like these point masses, but they're obviously not. Each galaxy has a lot of physics in there, and it's a rich new world. DES data, both the wide field and the deep field, provides a lot of information, especially when combined with external data sets. Within this group, there are several directions that we look into, carrying out kind of measurements of galaxies to come up with new value-added catalogs, looking at AGNs and quasars, and then connecting galaxy physics to large-scale cosmology. All right, again, some highlights. These are different value-added catalogs. On the left, this is work done by Sunny Chen, who used a convolutional neural net to generate this 200 million galaxy morphology catalog. So elliptical, spirals. Top right, this is a quasar catalog combining DES photometry with near and mid-infrared data. This is done by Qian Yang. And then you can see this is a completeness as a function of redshift and magnitude for these quasars. Bottom right, this is a catalog of low surface brightness galaxies. This is done by Dimitrios Tenoklides. So these galaxies are these ultra faint, not ultra faint, ultra diffuse galaxies that very hard to detect because they look very much like very low surface brightness and hard to detect and characterize. And their formation channel is very interesting because there's questions of how they live in clusters and what their masses are. That could help our understanding of galaxy formation in dark matter physics. So he compiled that catalog and is currently looking more into it. Another kind of big area that the Galaxy Evolution and QSO group looks at is this partnership with OSDES, which is our kind of Australian partnership. So this uses the Anglo-Australian Telescope AAT to follow up or monitor these 771 quasars over the whole 6 years of DES operation in the supernova fields. So that then gives a good cadence of both photometry and spectroscopy for these quasars that allows one to do various science. The thing I'm highlighting here is this reverberation mapping. So this is looking at kind of the variation of the quasars in both the continuum and the lines, and from that time lag to constrain the mass of a supermassive black hole associated with the quasar. And this is work done by Jiefu Yu, who basically performed this analysis using magnesium-2 light curves as well as the continuum. Okay, so the last thing on galaxy evolution is to use what we learn from galaxies to help cosmology. So here I'm highlighting 3 sets of analyses. On the left, this is looking at the very small scale information of galaxy-galaxy lensing, which tells us about how galaxies are connected to halos, which is a major systematics in like large-scale cosmology analyses. This is work done by Georgios Saknagas. In the middle, it's looking at color distribution of galaxies inside clusters, which help us constrain the quenching timescale of these galaxies. This is work done by Susmita Adhikari. And on the right, it's looking at deep field galaxies where we have multi-band photometry, and it helps us constrain the dust of galaxies that are hosts to supernova. And that helps us understand whether this magnitude gap kind of features seen in a lot of supernova studies are coming from dust. This is done by Cole Meldorf, Antonella Pomies, and Dylan Brown. Okay, moving further away, now we're looking at galaxy clusters. Galaxy clusters are the most massive objects in the universe. Aside from doing cosmology, there's a lot of other cool things you can do with clusters. And in particular, the cluster group really partners heavily with external data. I'm showing 2 kind of SC experiments, but there's also X-ray data as well. So the 2 things I'm going to highlight here on the top is looking at intra-cluster light. So these are very faint diffuse light in the galactic center. This requires really understanding background subtraction, understanding point source removal, This work done by Chang, who basically detected the ICL out to 1 megaparsec down to 30 magnitude per arc second square. So it's a very hard measurement, and with the quality of DS data, we were able to do this. On the bottom, this is looking at stacks of 1,000 galaxy clusters detected from an SC survey and looking at the distribution of mass and galaxies. And this is work done by Xin, who showed that the distribution actually agrees very well down to very small scales, which is somewhat surprising, but it's also a really cool paper. Okay, so that's like a fly through of the various science you can do with DES, but we actually also do cosmology, and we do it in many different ways. So here are the 7 ways that we typically advertise cosmology. So the large scale structure, Elisabeth will talk about counting galaxy clusters to constrain the halo mass function, looking at baryon acoustic oscillation, supernova 1A, strong lensing, kind of time delay, gravitational wave follow-up to look for basically standard siren or H0 measurements. So the plot here, Elisabeth will decode it. Basically, it's the large scale structure measurement. Plot top right is the year 1 cluster cosmology results, which highlights the importance of understanding selection functions in the cluster catalogs. Bottom right shows strong lensing measurement of H0, Hubble constant, using time delay measurements of basically quasar beam lens. This is a standard siren measurement from Antonella, looking at H0 constraints from gravitational waves. Bottom left, this is supernova year 3 results, constraining equation of state and omega matter. This is a DES constraint combined with CMB to form the smaller one. And the last one I kind of want to highlight is just that although there's many kind of known ways of doing cosmology, there's also new things that are being developed in DES. Here's just one example using the moments of weak lensing mass maps to constrain cosmology. This is work led by Marco Gatti. Okay, so that's kind of the end of my part. I'm not going to hand over to Elisabeth, who will tell us about the Y3 large scale structure cosmology. But I also want to, I also want to just highlight that, advertise that stay tuned for Y5 supernova and Y3 cluster cosmology that are coming out hopefully very soon. All right. Maybe it's a bit. I'm sorry, I was talking very fast.
One second, I had a brief screen share issue.
Yeah, if you want me to share, let me know. Good.
Okay, so after that grand tour of the DES universe, thank you, Chihway, I will fill in some more details and in particular methodological advances that the DES collaboration made on the way to the DES Year 3 cosmology results from large scale structure that many of you have probably seen on the archive in the last few months. Where I will focus on the BEO and 3x2 point analyses that recently finished. And of course, stay tuned for upcoming exciting Y5 supernova and Y3 cluster cosmology results. Especially these large cosmology analyses really are the work of many working groups, input from all across the collaboration, and hundreds of scientists, in particular many early career scientists, leading and contributing to all these advances. And in this part of the talk, I will highlight early career lead authors in bold going through. So I hope you will really see how cosmology results are indeed collaborative work. While we've learned to synchronize our paper writing, we're not good at synchronized speaking. So rather than having 200 people speak here, you're stuck with me for this part. So thanks for calling in, and good morning, good evening, or wake up wherever you are. The plan here is that we observe large scale structures through galaxies, and we particularly use 2 physical effects here. we have some galaxies in the foreground, but in DS we often call dense galaxies. And we use their spatial clustering to constrain cosmology. And then we have a second set of galaxies that we typically call source galaxies, for which we measure not only their positions, but also weak lensing. That is the fact that their shapes are distorted by passing through the tidal field of all matter between us and those background galaxies. And that gives them these coherent shape distortions. Of course, that then allows us also to probe the foreground lens galaxies or foreground matter distribution. First, I want to highlight expansion history constraints from baryonic acoustic oscillations. So that's the standard ruler, or rather the sound horizon imprinted in the galaxy distribution. So there we use galaxy clustering to measure the angular diameter distance. And in a recent paper based on year 3 catalogs, and the collaboration did that with a 2.7% error. This achievement is based on methodological advances again in 2 methodology papers, one describing the optimized sample selection, yielding a BEO sample of 7 million galaxies, roughly over the photometric redshift range 0.6 to 1.1. And then extensive custom mock catalogs developed for this analysis that, for example, are required to even estimate the error bars of the projected correlation function and do all kinds of systematic tests. So here on the right, you can first of all see the DES data points with error bars from these mocks in black. Then in red, the best fit template. And in orange also the same BEO template, but using the Planck, so early universe CMB cosmology. In terms of the cosmological interpretation then, you can see here our DES year 3 results in the context of other constraints on the angular diameter distance relative to the prediction from the Planck cosmology. So the prediction at Planck cosmology would be here the line at 1. And then you see constraints from BEO measurements in many different contemporary galaxy surveys. And the DES year 3 currently is about 2.3 sigma consistent with Planck. The other cosmology constraint that I want to focus on is testing lambda CDM by asking whether late time clustering is compatible with the predictions, assuming initial conditions, and in particular the amplitude inferred from the CMB. So that means that we will compare the amplitude of primordial scalar density fluctuations, AS, measured, for example, by Planck, with the amplitude of mass fluctuations today, measured from DES. And the main analysis that I'm going to focus on here is what we've been calling the 3x2-point analysis, where we now combine information from the background source galaxies, that is shape correlations or cosmic shear, galaxy clustering, that is the position correlation of our foreground sample, and the cross correlation, also called galaxy-galaxy lensing. This is a particularly useful analysis because cosmic shear, shown in black here, and the combined clustering galaxy-galaxy lensing measurement are subject to different systematics and also different parameter generacies. So we can first do these 2 splits of the data, check whether they are consistent, and if so, use them to break the generacies and self-calibrate underlying systematics to arrive at these most constraining 3x2-point results. However, it's a long way to get there. Here's how our DES year 3 analysis started. This is the result of discussions at the fall 2017 collaboration meeting, where we had just recently finished the DES year 1 analysis. And then our brilliant analysis coordinator, Michael Troxel, synthesized these discussions into this massive flowchart, where the label of the boxes right now is not so important. This is just to outline the complexity of such an analysis. And you can imagine each of these arrows requiring communication between different groups. So that's how it started. And here here is how it's going. That's now an illustration by Alex Amon, showing you the way from pixel level data in terms of wide field images, deep field photometry, to 3x2 point cosmology, and the different papers along the way, going through shear measurements and null tests, point spread function and modeling to the shape catalog, and then another branch going through survey selection and redshift calibration to redshift distributions. And all of this eventually leading to clustering and cosmic shear measurements, and a bunch of theoretical developments on the covariance, simulation development, modeling to finally arrive at a cosmological interpretation. And in the remaining slides, I will highlight some of these methodological developments. If you want to get a full story, just turn to the archive. All these developments have been posted in 29 supporting papers, as well as then, of course, the final cosmology result. So first of all, redshift characterization. In order to do cosmology with both of these galaxy samples, we need accurate characterization of the redshift distributions. And for the lensing sources, we do this using 3 independent sources of information. We use photometry or galaxy clusters, galaxy colors, which are then interpreted using a self-organizing map algorithm described in a beautiful paper that by Justin Meltz and Alex Alacon. Then we also use galaxy clustering, that is their positions, in particular the cross-clustering algorithm. In another ECS-led paper, Gatti and Giannini. And then we also use lensing or shapes in the form of shear ratio measurements. And these 3 methods provide important cross-checks. I briefly wanted to highlight the self-organizing maps here, which has been one of the huge methodological developments for the DSE3 analysis, where our self-organizing maps is a Bayesian redshift scheme that uses deep fields observed by DES as an intermediate step to bridge spectroscopic redshifts for a very small sample of galaxies to the DES wide field galaxy sample. And in particular, we use artificial galaxy injection with the Balberg algorithm to characterize how these deep field galaxies would look like in the noisier wide field conditions. The next important ingredient, of course, is galaxy shapes for weak lensing, where for DSES3, we have shapes for over 100 million galaxies. And the illustration here on the left shows you the convergence map from the science verification era of about 3 million shapes through the SE1 with about 35 million shapes to the SE3, covering this oddly shaped footprint. On the shape front, the key improvements over the SE1 are more accurate point spread function modeling, improved astrometry, an expanded suite of null tests, and shear calibration using realistic image simulations that now newly characterize the impact of blending on both shear and redshifts. Another heavy lifting on the methodology front led by Neil McCran, another recommended paper. Then for galaxy clustering and as lenses for galaxy-galaxy lensing, in year 3, we now use 2 different galaxy samples. One called Red Magic. That's a large red galaxy selection as it was used in the year 1 analysis. Here, the individual redshift distributions are stacked and then validated using cross-clustering. Then new in year 3, we also have a magnitude limited galaxy sample. So that's a bright galaxy selection where the selection cut is defined using machine learning of photometric redshifts And these photometric redshifts are then also validated using cross-clustering, resulting in 6 redshift tomography bins with the redshift distribution shown here. And again, this work is based on several essential papers led by early career scientists, highlighted here in bold. One more important ingredient for galaxy clustering is systematics control. That is, we have to ensure that observational systematics, which induce spurious fluctuations in the apparent galaxy density, are removed. And we do that with an iterative process, reweighting the galaxy sample through a relation calibrated from data, such as survey property maps and also astrophysics systematics. And the plot here shows you the importance of this observation systematics correction, showing you galaxy clustering is a function of angular scale, where the red crosses are the raw measurements. And then the gray symbols show you the clustering measurement after correction for observation systematics. This angular clustering is then analyzed on large scales, basically providing a constraint on clustering amplitude, that is galaxy bias times cosmological amplitude. And in combination with galaxy-galaxy lensing, we can then calibrate linear galaxy bias. To fully take these 3x2 point measurements to cosmology constraints, we then perform a Bayesian analysis within a given model M. To do so, we need a few more ingredients. We need a data likelihood and data covariance, for which the requirements are laid out beautifully in a paper led by Oliver Friedrich and collaborators, showing that a Gaussian data likelihood and Halo model covariance are sufficient for this DSE3 analysis, but also pointing out areas where further research will be needed for future analyses, such as in LSST. Then we need a model covering both cosmology and astrophysics, and corresponding parameters and their priors. Furthermore, we need criteria which measurements we can combine and under which conditions, again laid out in 2 ECS-led papers by Cyril Du, Pablo Lemos, and Marco Raveri. And we need a blinding scheme to minimize observer bias. So implicitly in this slide, we now decided how to model astrophysics and cosmology and in which prior range. Then our best test for this 3x2 point analysis is with synthetic skies, where n-body simulations are our best model for the nonlinear growth of structure. And we want to use these to provide convincing tests of analysis robustness. So we then need simulations that include realistic relations between cosmological observables and quantities used for sample selection. We also need high enough resolution to model all measurements accurately on the scales included in our analysis. And we need these simulations at many times the volume of the survey to really make statistically robust statements. And I point to the paper led by Joe DeRose, describing the generation and validation of these simulations. With these mock catalogs, then we can demonstrate the catalog to cosmology pipeline by doing all the measurements as we will do on DS data on the full suite of simulations, and basically carry out end-to-end tests starting from redshift calibration and correlation function estimation all the way to cosmological parameter posteriors. And the plot here on the right shows you cosmology constraints, both from the mean data vector of all simulations and from a synthetic data vector generated within our model. So any offsets between these two contours would hint at shortcomings of our theoretical model. And this shows you that these types of systematics are well under control. Still, at this point, we're about 27 papers deep. And getting to that point, we've made a lot of choices in making the catalogs, in the correlation function measurements, which data points to include in the analysis, and running many trial chains to get our inference diagnostics going. Of course, we want to make sure that the choices that we make at each of these steps don't bias our final constraints through observer bias. Hence, we implemented a 3-stage blinding scheme where catalogs are rescaled by an unknown factor. Correlation functions are transformed corresponding to an unknown change in WCDM parameters, as laid out in a beautiful paper led by Jesse Muir. And the axis of posterior plots are offset by an unknown amount, at least until all data vectors and modeling choices were frozen and we agreed to unblind. We further also finalized the list of model tests and which combinations with external data to pursue before unblinding. Sounds nice. In practice, these last steps were somewhat of a roller coaster ride, as data, as always, is different. However, let's get to the results. First of all, the internal consistency of DES cosmology results. Well, we have 2 correlated cosmological probes, cosmic shear, shown here in blue, and a combination of galaxy clustering and galaxy-galaxy lensing, shown in orange. These are 2 independent splits of our 3x2 point data vector, and we find consistent results from them on the clustering amplitude S8 and omega m, the matter density. Here, as shown in the introduction, cosmic shear is most sensitive to the clustering amplitude, and galaxy clustering tangential shear are more sensitive to the total matter density. As these 2 splits of the data are consistent, we then combine these into the 3x2 point analysis, shown here in black as the joint constraints. This result provides a factor 2.1 improvement in signal to noise compared to DES year 1, and parameter values that are probably best read off the key paper, that is DES Collaboration 2021, a paper from late May. Of course, then the big question is, where does DES 3x2 point stand relative to other surveys? And for that, we start off by comparing 3 independent data sets. Our DES 3x2 point analysis shown here in black, and then the combination of other low redshift non-lensing data, that is supernovae 1A, BO, and RSD, and the Planck cosmic microwave background constraints. These are highly complementary measurements and highly complementary physics, and we find a common parameter space at about 1 sigma confidence limit. We can, since each of these sets is consistent with the other 2, we had decided before unblinding already that we would combine DES and the other complementary low redshift probes to test consistency with the CMB results. So that's shown here, combining black and orange into the purple contours of all the low redshift measurements. And we find these to be consistent with Planck at 0.9 sigma or P of 0.34. As the last cosmology result that I wanted to highlight, going beyond 3x2 point, is the combination with galaxy clusters in year 1. As this is one more important methodological step towards the static probes analysis in Elsa's team, combining all the available information. So in this paper here, led by graduate student Chunhao Cho, we found cluster cosmology constraints from abundances in large-scale 2-point statistics, combining cluster number counts, large-scale cluster lensing, cluster clustering, and cross-clustering between clusters and galaxies. The joint likelihood analysis, again, was validated on DES-like mock catalogs. And in this setup, the cluster mass relation is calibrated from large-scale clustering, accounting for the selection biases. As a result, the DES cluster cosmology constraints with this method are consistent with the DES year 1 3x2 point results, showing you here in black the DES year 1 3x2 point analysis, And in red, this joint analysis now including cluster counts, where importantly, most of that gain in constraining power really is from including number counts rather than from including additional 2-point statistics, really pointing towards the potential gain of doing joint analysis of galaxy shapes, galaxy positions, and galaxy clusters. Okay, that was a lot of cosmology. Now we will conclude with some lessons from DS, where of course we should start with several caveats. First of all, DES combines both the project and science collaboration aspect of Rubin. And we are one science collaboration covering all of the science areas, as particularly shown in Chihway's part of this talk. So our organization and our workflow is somewhat different. However, I think it will generally apply that simulations are an absolutely crucial tool and the best preparation there is for many analyses. But data is going to be different. In particular, there will be unknown unknowns that we simply cannot put in simulations beforehand. Many of the projects highlighted here are large science analyses, which are a science opportunity. I hope I've shown you many examples of early career scientists advancing the field at multiple fronts with cutting edge papers. But these analyses are also communication challenge. The number of messages or telecons appears to scale superlinearly with the number of people or papers. We've also learned that crucial infrastructure tasks are less daunting if identified early and given dedicated effort. Interactions for us intensified massively once data arrived. While this is difficult at the moment, long term, we believe that in-person interactions, at least once in a while, are absolutely critical. And for example, help to humanize people again that one may have disagreed with on Slack, especially when tension runs high. So in summary, let's get ready for surprises, thrilling, annoying, and everything in between, and intense collaboration. Thank you.
Yay. Thanks, guys. Give a warm Zoom round of applause, and also in the Slack. That was excellent. Thank you very much. We've had some questions come in while you were talking, but mostly they've been answered so far on the Slack, but I can see a couple of new ones. So everyone go ahead, write your questions in the Slack, in the Zoom, or raise your hand and we'll cycle through and do some questions. So I have one question on the Slack that asks, in the gorgeous sky maps that were shown, including galaxy distributions, there are some round regions excluded. Are those from very bright stars? Should LSST anticipate being unable to utilize such large regions, or will our short exposures counterbalance the larger telescope aperture?
Elisabeth, do you want to take that? Or...
So let me just briefly try to find the correct slide for that.
Okay.
I guess one of these.
Yeah, then maybe the mass map also has some holes, but yeah. And those round holes.
I must admit, I don't know what all those round holes are, but the big ones here.
Yeah, they should be star masks. And I think the question of whether LSST it has shorter exposure, but it has bigger aperture. So I can't predict if it's going to have the same level of holes, but I think that's something that people have thought about.
It'll be worse because you're going to lower surface brightness. So in G-band HSC, if you do a naive mask, you lost 30% of the sky. Now, you can get around that by a more aggressive sky subtraction or by subtracting the wings of the stars. And what we're planning at the moment to do is to subtract explicitly the wings of the stars. In the cores, of course, there's no signal to noise and there are ghosts and awful things. That's a tiny area. But if you process it the same way as you process DES, you'll almost certainly get larger holes in LSST.
Robert? Alex, did you want to answer that?
Yeah, it's just a comment that it's not actually the wings so much that we're subtracting as it is the scattered light. And Robert, I remember a conversation we had, the expectation is that the scattered light in LSST should be better. But as Keith points out, everything is going to be assessed during commissioning. Is that correct?
Scattered light from what? The telescope or from the atmosphere? The knee wings are really up there too.
So these are reflections off of the lenses as well as, yeah. So
Yeah,
off the optics. Yeah.
They're the ghosts and ghouls. Yeah.
Correct.
Great. Thanks both. We have another question from the Slack. This one, what discovery opportunities are you most excited about with LSST in the context of all the DES results that you just shown in any area, or if you want to stick to cosmology, just for cosmology?
I guess I'll give my take and then Elisabeth can give her take. I mean, I think one major difference between LSST and DS is the time domain that is like very different. So DS wasn't designed with that in mind. So I think that will be the most, I feel like, low-hanging fruit that I would think will come out of LSST. But I don't know if Elisabeth wants to comment on cosmology.
No, I agree that time domain will be the most exciting new thing, but it has been really incredible science experience getting the 3x2 point cosmology to the point where we are right now, and just thinking about the huge improvement in data quality and area. Weak lensing isn't done, nor clustering. So at that point, we will definitely get a statistical and systematically very constraining answer on whether there is an SA tension or not, which is definitely something that I'm quite excited about working towards.
Cool, thanks both. We have another question from Slack that's been very upvoted, but it's a little long. So if Michael Woodvasey, if you'd like to just unmute and ask your question yourself instead of me reading it out.
Sure.
Cool.
So one thing in large projects is that there seem to be a core people who need to be at all meetings all the time, right? See our inability to divide into actual 6 parallels during a collaboration meeting or even project community workshop. Did you have any success in trying to better define things and define interfaces and groups? Or can you sort of quantify the trade-off between the efficiency of everyone, or some people knowing all the things and being at all the meetings and thus spreading knowledge, versus the inefficiency of those people having to be in meetings all the time instead of getting stuff done, versus the other direction of having well-defined areas, but understanding that you will have duplication of work and you will rediscover things and you'll apparently have inefficiencies from that side. Can you offer any thoughts on that?
Can you paste the whole question into this chat here as well, please?
It's on Slack if you.
Okay, thanks.
Yeah, but Elisabeth, maybe you can comment on like the Y3 cosmology structure and do you think it works?
I still think that we did well in the end in terms of carving out a lot of separate papers, which is absolutely essential, I think, to keep enthusiasm high. I mean, mostly we really are competing for time off these early career scientists who could be working on something else. So I think that should definitely be one of our top considerations before going in with a simple project optimization mindset. So there will be overlap, and maybe not all interfaces will be completely defined early on, but definitely breaking it up into some intermediate chunks where it was clear that those groups would interact day to day and maybe only every other day with another big block. That definitely helped. For a while, we had daily year 3 calls with 50+ people on the line, which definitely was not the most optimal organizational structure.
Yeah, it's a hard problem. I think LSSU would just be even bigger. So
yeah, and also this only ended recently. Ask us again in half a year and maybe over a beer.
Excellent. Well, thank you both, Elisabeth and Chihway. There's a couple more questions sort of in the Slack, but it looks like they're being answered in the Slack. So maybe just go check in on them, see if you can add anything more to the answers. And with that, we'll end our science keynote plenary. Let's give another round of applause to Chihway and Elisabeth as you go. Thanks very much, you guys, for being here. It was excellent.